Hi everyone, I am conducting this session to further build on our knowledge and understanding of simple linear regression. Before uh, building further, what I will do is I will just refresh uh, from the start. So we started dealing with two variables at a time um as a part of our bivariate analysis, and we learned few concepts of covariance, correlation. These are the measures of associations. Measures of association, and in particular, we are interested in rho. That's what we call as Pearson product moment correlation. Pearson product moment correlation. There are way too many correlation types, so we are not going to delve into them. And we also know that correlation is standardized covariance. So the formulae for those are available on our website, and you can read it from there. How to calculate correlation for sample, how do you calculate correlation and covariance for the population, and so on. What we're going to do is we're going to understand the concept of regression and and uh, and see how we can mathematically uh, capture the intelligence embedded in variable x to explain variable y. We know that we have this bunch of variables in x, bunch of variables in y. The measure of association is rho. We have already seen that, how to calculate it. We know that rho uh, values are between -1 and +1. There are no hard and fast rules in terms of what is a strong correlation or a weak correlation. So let me call the strong is strong negative correlation on one side, strong positive relation on other side. And then let's say this is 0, so we can see that there may be some which are closer to 0, which will still say no correlation, or we say random. I mean, x and y are randomly associated with each other. You cannot use x to explain y. And here you may call it as moderate correlate, moderate negative, moderate positive. There are no hard and fast rule in terms of what are these cutoff values. But as a thumb rule for a, I mean, depending upon what kind of data you're dealing with, but typically for a panel data, you may consider zero point 0.7 to be very strong until 0.4 you may consider to be moderate. You can consider 0.3 as well, so that's perfectly okay. So negative 0.7, then positive 0.4, positive 0.3, positive 0.7. This is of course 1 and -1 at the border. So we have some idea of that there is something in y which can be explained using x. So this is the concept that we're going to extend and capture this more quantitatively. Beyond just association, we move to the concept of explanation. So let me just clear this and and switch to my laptop, where I will take some example and explain to you the concept of regression. So let me switch. All right. So here I am, and let me come to the website. This is our website. We know the formulas for covariance of population and sample, correlation of population and sample, and we would come to chapter 10. And how do we kind of come to these y estimates? So let's take a very simple example first. X and Y and these employees. So let me start from the scratch. So let's say these are my employees. They have some X score and Y productivity. A, B, C, D. And their X scores are 12, 14, 17, 16, 11. 14, 17, 16, 11. And Y the productivity 55, 63, 67. 55, 63, 67, 70, 51. That's what I recall. Yep, 751. So these are our X and Y. And so let's first thing to let's visualize these two data sets together. So I will go to insert, scatter plot, and select the scatter plot from here. So this has selected by default in this fashion. So let me quickly. So what it has done, it has picked up these 1, 2, 3, 4, 5 values from here and plotted the X and Y on it. But what we want is we want to only capture these two, and here is my Y values and here is my X values. So let me quickly look at it. Okay, so you are able to change what is displayed on the data set, on the chart. I can move it to a separate dedicated sheet so that I can see um, it in a separate sheet. And since these are all clustered in this small little area, so I may put a boundary of 10 to 18 and 50 to maybe 75. So what I can do is I can just change these axis minimums. So that's the minimum that we have. It has automatically changed to 75 there. And similarly change it to 10. It should automatically adopt it to, yeah. All right. So here is our the data points. If you want to enlarge them, you can do that as well. Yep, all of them are selected. Come to this marker and marker options. Okay, I can increase the size, change it to a cross. Maybe if you want to change the color. This is border, this is fill, so we will pick up the color from here and let's see. All right, so no fill. Marker, no fill. We got a this, we want to increase the thickness and select the color red. So we have changed it from the dots to crosses, and I see that as X increases, Y increases. So we see the points in certain order, in a certain direction. So what I can do is, I see that there is some association between x and y. By knowing the x, we can determine y, or we see that the change in y can be explained by change in x, because they're all changing broadly in the same direction. Now let's look at how do we quantify this. The other part is, what I can do is I can right click it and add the trend line, which will help me fit the equation, the least square equation on it. This is small, so I will just go to home, change it to maybe 24, and position it where I can read it clearly. So we see that the best fitting line is the one which says 3 times x plus 19.2. So we see that we can do y estimate, and let me introduce you to some more things that you learn in Excel. So we want to have y hat, which is our estimated. So I choose this, I make it y hat. So that's my estimate. You can increase the font size. Yeah, that's sufficient. And we know that the formula is 19.2 plus 3 times x. So we can determine all the y hat values, right? So let's do some basic calculations here. Mean, standard deviation. I want you to learn how do we do this using our Excel. So I can just go here, click average, and I get the average. Just to clearly demarcate the data area, I can just fill it with some color. Okay, this should suffice. Let me just fill this with another color, so that we know that these are the estimated values, this is the original data set, and these are the mean. I can copy paste this, it will come here, and we see that the estimated value of y is 61.2. I can calculate the standard deviation. Standard deviation for population versus sample. We'll use the sample because we are saying that we have only sampled 5 employees. From there, we are building the estimate for the rest of the employees. So we will take the standard deviation, specify the values, and we can copy and paste it. We can format it to make it look a little nicer. Now we are able to explain some value or estimate some values of y using the values of x, right? So let me go back to the fundamental, and let me explain to you what is it we are trying to accomplish here. Let me start sharing. Let me stop the share here and come back to my whiteboard. All right. So we take this example of y. Let me take the same example of the dollar amount of tip that you receive in a restaurant. So let's say y is dollar tip amount. And let's say I take 3, 7, and let us say 5 as the 3 tip amounts that were received on the 3 previous orders, order 1, order 2, order 3. I'm trying to figure out what's my expected value of tip on the 4th order. In the absence of any intelligence, what I would do is I will take this and see 3 plus 5 plus 7. So that's 15 divided by, so my expected value of y is 5, $5. But if I tell you the x, the order amount or the value of the order, and let us say if I say that the values were these, and let's say if I ask you, let's say the new value is 63. So, so in the absence of any intelligence, your expected value of the order of the tip on the order is $5. Uh, so what I'm trying to estimate is, if I know the value of the order, do I have a better estimate of y? So here I say that people generally tend to round it off in multiples of $5 or $10. So let's look at it. This works out to 30. This works out to 65. This works out to 30. So in case it is 63, what is your best estimate here? People are typically giving you 1/10 of the tip. So the value hovers around plus minus 10%, plus and minus of 10% by a few percentage points. So here estimated value would be 7, because that gives us a value of 70. Because to get a value of 65, 2 is very unlikely. To get a value of 75, the value is 12, which is also unlikely, but 7 is very likely value. So here we have captured some intelligence, because so now we have moved from 5 to 7 because of our knowledge of the order value. Now we are going to look at how do we quantify this in our regression through a regression equation. So I come back to our Excel. So here, in the absence of any intelligence, our estimated value of productivity is 61.2. But if we know the dexterity score of the employees, okay, this example I picked up from here. So you can read about how we arrived at the values. And you can see that this beta, the B1 and B0, the slope and the intercept can be determined using our trend line and displaying the values. Or if you want to do it manually, in the in the in the important formulas of the previous week's upload, you will see the formula is available here. You can use it to calculate this. So now we have come to these values of y hat. Now we capture how do we quantify these. All right. And yes, of course, we can calculate the correlation here. The formula is correl. So we specify first array, second array, and we get the value. So here it is. So you can express it as a percentage as well if you feel like, or else keep it as is. So the correlation coefficient is 0.95 or 96. So that leads you to say that there is a strong positive correlation, and which is pretty much evident in the chart as well. So now what we will do is we will calculate what is the total variance, which is the total variance of y. Then we look at the total variance which we are able to explain, and we call it as the total variance associated with regression, and total variance, which is unexplained, which is the error. Now the total variance will be explained with respect to, I will have to use our equation tool here. I'm not able to click, so let me move it around and now click. Oh, since I am inside and I've double clicked here, I'm already in the cell, so that will not be active. To escape this, for this to be active. So what I want to do is I want to capture y minus y bar, and then we capture it in form of square. So I have this option, or I can use this. Capture it here and put it here. So that's my SST, the total variance. And the way I will calculate is y minus y bar square. I can, okay, I need to ensure that I am using 61.2 at every time, so I have to put these dollar signs to maintain the absolute referencing. And when I double click this, I get to see the variance captured, what y with for each of these values. Then I sum that up. That's my total variance in y. Now there is an amount of variance which you are able to explain because of x, and that would be okay. I need to come back again. Insert equation. Let me start from equation wherein I take the square term first. Take within the bracket. I'm looking at the explanation which comes from the y hat minus y bar. So that's the amount I'm able to explain with the intelligence that is embedded in X, right? So this, I calculate this. This is my estimate minus y bar. Press the dollar. So how do you get these dollar signs? Either you press F4 on your Windows machine, or you press Command T on your Mac machines. So this is the amount of variance that I'm able to explain using the intelligence embedded in X. Now there is an amount which we are not able to explain, so that's the deviation between y hat and the actual value of y. So let me just quickly just copy, paste, and try to, so that's y minus y hat. All right, so that's the error term, right? So it's equal to y minus y hat. So this is the amount of variance which I'm not able to explain despite my modeling effort. So what I've got is, I've got the total variance of y, I've got the variance of y which is explained by x, and I've got the variance of y which is not explained by x. If you look at the sum total of these two, which you can observe here, 256.8, which is same as the total variance. So your R square, or the coefficient of determination, is the proportion of variance which is explained by the total as a proportion of the variance explained by your model. So here, so this is your R square. I may want to again use the equation and use the R square. So I can say that R square is equal to this. All right, so we have been able to determine the R square, and the same R square which we determined using the chart here, 0.911. So we have been able to make an estimate of y and also quantify the amount of variance in y we are able to explain using x. So that's R square. Now the point is, these values are your point estimates, because the y estimate itself would have its own variance, right? So let's refer back to our chapter. So we have been able to estimate this, we have been able to estimate this, and get the point estimates of y here. So we've been able to plot this equation. So now we have got the y estimate. We want to find the interval estimate of this y. So this is the mean of y. These values are the mean of y given x. So for every given x, there is a expected value of y, and the expected value of y will have its own variance, or through which we are or the uncertainty which we capture using the interval estimates. So now we will move to making the interval estimates, and we can now talk about calculating the standard error of the estimate for our y estimate, and that's given by y minus y bar whole square divided by n minus 2. So this is the amount of error that we have captured. So when we use this, so we want to calculate the standard error of the estimate. Okay, let me bring it here. Standard error of the estimate of y given x values is equal to. So this is the total error around y, and we can calculate this. So this is the sum of the error, and is equal to, okay, oh, okay, is equal to divide by n minus 2, that is 3, power 0.5. Okay, so we are able to calculate the standard error of the estimate, which is 2.757 by using the formula which is given here. Now using this, we will be able to now build the interval estimate of the point estimate of y. So each value of y hat will come with its respective interval estimates. Now there are two sources of uh, of uncertainty here. One is the uncertainty because of the unexplained variance or the error, and the other is these values 3, which is your beta 1, and 19.2, which is beta 0. Both of them themselves are estimate of the population parameters. So we will have the confidence interval around y, and then for each individual observation we will account for the uncertainties associated with these beta 0 and beta 1 to come up with the prediction interval. So let's go about estimating those. So we will use the t table for calculating this. So we know the y hat. We can calculate the t n minus 2 at 95% confidence interval, and we have already seen how do we calculate this, and then we use this formula to do the rest of the calculation. So the derivation of this formula is outside the scope. So we will need to kind of calculate the xi square, xi sum whole square, x minus x bar, and so on. So what we will do is I will find x minus x bar. Okay. X minus x bar square. Let's kind of calculate the square itself. Okay. I'll go back to my equation. All right. So we have already calculated x minus x bar power. All right. And xi square. So that's simple. X so Yes. So now the margin of error will be Tn minus 2 at alpha. So what I will do is T value calculator. We can always look back at any table and calculate it from there. So degrees of freedom will be 3 and minus 2, and the significance level we are looking at is 95%. Calculate, and we are going to use two tails, so this is 3.1824. So your T 3.1824, 3.182, maybe I just use this. So I've got, so what all I need Tn minus 2 alpha by 2. I need the standard error of the estimate, and I know this, so I can calculate now.